Hello everyone, my name is Dan Hart and today I'm going to be talking about El Niño Southern Oscillation, known as ENSO for short. So this presentation is going to cover ENSO. It's a crucial climate phenomenon with profound effects on global weather and climate. This presentation is a broad overview for a non-technical audience, so nothing too complicated. It's not aimed at expert meteorologists. The goal of this presentation is to define ENSO, describe its phases, and discuss global impacts and future implications. First of all, let's define ENSO. So ENSO stands for El Niño Southern Oscillation. It's a natural climate pattern that occurs in the Pacific Ocean but influences weather and climate patterns globally. It involves the periodic fluctuations in sea surface temperatures and atmospheric pressure across the equatorial Pacific. The phenomenon has two main components: El Niño, a warming phase, and La Nina, a cooling phase, and a neutral phase in between. These fluctuations are accompanied by changes in winds, ocean currents, and atmospheric circulation. So ENSO is not a single event, but a reoccurring climate pattern. The cycle of ENSO includes both oceanic and atmospheric changes, making it a coupled phenomenon. ENSO has global significance. Although it originates in the Pacific, its effects are felt worldwide. So there are three main phases of ENSO. First of all, let's look at El Niño, represented by the map at the bottom. This is characterized by the warming of sea surface temperatures in the central and eastern tropical Pacific Ocean. This phase often leads to significant weather changes across the globe. La Nina, represented by the map at the top, is characterized by a cooling of sea surface temperatures in the same region. This phase often produces opposite weather effects to El Niño. And in between, the neutral phase, the map in the middle, this occurs when sea surface temperatures are near their long-term averages and the atmospheric circulation is close to normal, so neither El Niño or La Nina conditions are present. The ENSO cycle moves between these phases typically every 2 to 7 years. Each phase has a distinct atmospheric and oceanic conditions, leading to different weather patterns around the world. The transitions between the phases are closely monitored by climatologists as they can signal upcoming changes in global weather patterns. These phases are also influenced by the interaction between the atmosphere and the ocean through pressure systems like the Southern Oscillation, which refers to the seesaw pattern of air pressure between the western and eastern Pacific. These changes in ocean temperatures and wind patterns affect weather systems globally, influencing rainfall, droughts, and storm patterns across many regions. The air pressure changes driving the phases of ENSO are caused by complex interactions between the atmosphere and the ocean surface temperatures in the Pacific Ocean. And here's how. When trade winds weaken during El Niño, warm water piles up in the central and eastern Pacific, which raises sea surface temperatures. This warming changes atmospheric pressure, with lower pressure forming over the warmer waters. The opposite occurs during La Nina, when strong trade winds push warm water westwards and cooler water in the east leads to higher pressure over that region. The Walker circulation, this is a large-scale circulation pattern along the equator where air rises over warm water and sinks over cooler water. The Southern Oscillation refers to shifts in this pattern. During El Niño, rising air over the eastern Pacific leads to lower pressure, while the western Pacific experiences higher pressure. During La Nina, the pattern reverses, with lower pressure in the west and higher pressure in the east. So there is an ocean atmospheric feedback. Warm sea surface temperatures reinforce the weakening of trade winds, which in turn lowers atmospheric pressure further in the eastern Pacific. This feedback loop drives the air pressure changes during both El Niño and La Niña phases. Thus, changes in ocean temperature drive shifts in air pressure, which are central to the development of ENSO phases. So what happens during El Niño? During El Niño, sea surface temperatures in the central and eastern Pacific are significantly warmer than average. The warming can extend across thousands of miles. Normally trade winds blow from east to west across the Pacific. During El Niño, these winds weaken and in some cases may even reverse direction. The weakening of the trade winds leads to a shift in the water circulation, a key component of the tropical atmospheric circulation. This causes changes in rainfall patterns with increased precipitation in the central and eastern Pacific and dry conditions in the western Pacific. So the weakening of the trade winds disrupts the normal upwelling of cold, nutrient-rich water along the South American coast, which can devastate local fisheries. The altered atmospheric circulation leads to changes in weather patterns far beyond the Pacific region, affecting climates globally. Impacts include increased rainfall in the southern United States and droughts in Southeast Asia and Australia. In contrast, La Niña is associated with cooler than average sea surface temperatures in the central and eastern Pacific. During La Niña, the trade winds strengthen, pushing more warm water westwards and allowing cooler water to upwell along the South American coasts. The water circulation intensifies, leading to stronger convective activity, that is rainfall, in the western Pacific and suppressed convection in the central and eastern Pacific. The strengthening of the trade winds during La Niña enhances upwelling, which benefits marine life and local fisheries along the western coast of South America. La Niña often leads to wetter than normal conditions in Southeast Asia and Australia and dry conditions in the southwest United States and South America. La Niña can also influence the frequency and intensity of hurricanes in the Atlantic, often leading to a more active hurricane season. During neutral phase, sea surface temperatures in the central and eastern Pacific are close to their long-term average. The trade winds maintain their normal strength and direction, blowing from east to west across the tropical Pacific. Weather patterns during this phase are generally consistent with seasonal norms, without the significant anomalies seen during El Niño or La Niña phases. The neutral phase is often a transitional period between El Niño and La Niña, though it can last for several months or even years. The neutral phase may seem uneventful, but other climate drivers, such as the Madden-Julian Oscillation or the North Atlantic Oscillation, can still lead to extreme weather events. Let's look at the global impacts of El Niño. They're different from season to season. The maps on the right-hand side, the one at the top, are typical impacts from December through to February, while the bottom map is typical effects from June through to August. El Niño often leads to increased rainfall and flooding in the southern United States and parts of South America, while causing droughts and wildfires in Australia, Indonesia and Southeast Asia. The warming of the ocean waters during El Niño disrupts the marine ecosystem, particularly off the south coast of South America, where the reduction in upwelling of nutrient-rich waters can lead to a decline in fish populations. The impact of El Niño can be economically devastating, affecting agriculture, water resources and fisheries. The resulting weather anomalies can lead to crop failures, reduced fish catches and increased natural disasters. Examples of past El Niño events include the 1997-98 El Niño, which caused widespread weather-related damage and had severe economic impacts across multiple continents. The human and economic toll of El Niño includes increased food prices, health issues related to flooding and droughts, and the cost of disaster response and recovery. And moving on to the global impacts of La Nina, again the map at the top are the typical impacts from December through February, and the map at the bottom represents typical effects June through August. So La Nina typically brings wetter than normal conditions to Southeast Asia and Australia, often resulting in flooding. In contrast, it can cause drier than normal conditions in the southwestern United States, parts of South America and East Africa. La Nina conditions can lead to an increase in the number of hurricanes in the tropical Atlantic Ocean due to a weaker wind shear and cooler ocean temperatures in the Pacific. While some regions may benefit from La Nina, there's cooler weather and wetter conditions, such as increased crop yields in Australia. Others may suffer from droughts or excessive rainfall that can damage crops. One example of a past La Nina event was the 2010-2012 La Nina, which contributed to severe flooding in Australia and droughts in the southern United States. Climate models indicate that global warming may alter the frequency and intensity of ENSO events, although there's still much uncertainty about the specifics. As the climate changes, predicting ENSO events becomes more challenging as the baseline conditions, such as ocean temperatures and atmospheric circulation patterns, are shifting. Climate change may exacerbate the impacts of ENSO events, potentially leading to more extreme weather patterns such as stronger hurricanes, severe droughts, and heavier rainfall. Some studies suggest that global warming could lead to more frequent and intense El Niño events. Other research indicates that the overall impact on ENSO remains uncertain. There are significant challenges that climate change poses to ENSO prediction models, which rely on historical data which may no longer be fully applicable in a warming world. And how is ENSO monitored? Satellites play a crucial role in monitoring sea surface temperatures, ocean currents, and atmospheric conditions, providing real-time data that is essential for predicting ENSO events. There is an extensive buoy network across the tropical Pacific monitoring ENSO. These buoys are strategically placed across the region to measure sea surface temperatures, ocean currents, and other important variables. In addition, advanced climate models use data from these satellites and buoys and other sources to simulate the ocean atmospheric systems and predict the onset, duration, and intensity of ENSO events. So moving on to preparing for ENSO events. ENSO predictions are used to develop early warning systems that alert governments and communities to potential impacts such as droughts, floods, and extreme weather events. Preparedness plans are essential for reducing the risks associated with ENSO events, including measures such as improving water management, strengthening infrastructure, and developing emergency response plans. Effective response to ENSO events requires a coordinated effort at local, national, and international levels. Policies must be in place so that resources are available to respond to and when ENSO-related disasters occur. So to summarise, ENSO is a powerful climate driver that has significant impacts on weather and climate around the world. The three phases of ENSO, La Nina, El Niño, and neutral, each have distinct effects on global weather patterns, influence everything from rainfall and temperatures to storm activity. As the climate continues to change, ongoing research and monitoring are crucial for improving our understanding of ENSO and enhancing our ability to prepare for ENSO events. I'd like to thank you all for your attention.